Hello, Jeremy.
Hello.
How are things?
All right. Nothing too crazy going on now.
Nothing too crazy, yeah. So usually it goes crazy, and now today is better. Huh?
Surprisingly, I think this semester is ending a lot better than it started out for me anyway. So I'm actually looking forward to next semester and all that. Hopefully coming back to school and not being stuck at home.
Okay, good. At least that's the plan, and it seems like everything is going as per what everyone wants. Let's hope for the best. So, will you be still working next semester, or how does it work for you?
Well, Dr. Mazumdar said something about possibly asking me to do some paid research there, so I might not have to work at McDonald's at least too much. So
Perfect. Okay, that's very good news. Yeah.
yeah, I don't know. I almost couldn't even believe it whenever he because I had messaged him about class and stuff and worrying about like how things are going, and then he kind of shot that back at me, and I was like, oh well, crap. I guess it's not too bad.
Okay, good. Okay, that's good news. Okay. Hello, Matt. Hello, Curtis.
Hello.
Good. Okay, let's see. Yeah, where's Bowden? Okay, let's begin. Your homework 10 that's due on Monday. You will need the result of today to start with the homework. There's only one question in there, but you can as well start over because I think the expression itself is there in the homework. So that's just for your information. But you can as well, since today you will see the result. It's okay. Did anyone check the time by any chance for the exam? Do a check on it when you get a chance. Okay, we were we actually derived the radiation fields, the expressions for that. And let's today proceed and do that for a specific scenario. We had a very general expression. Today we can do it for a specific scenario. And before that, I think, I want to change, let me go back and write it down. Yeah. So what we talked about is, so these are radiation, or you can say radiation fields, electric and magnetic fields, because things are moving around. So what we said is that if you have charges moving around in a certain region, so these are charges, lots of charges, let's say, they're all going here and there as a time-dependent scenario. But if you were to observe things relatively far away, and the idea is that in this particular regime, in statics, we notice that there is only 1 over r square potential, or 1 over r square electric field at r tends to infinity. But we notice that in this way, we can even get 1 over r potential. And that's what is called radiation fields. And we said they are described by the condition that if the t prime was a characteristic time of the system, this is very much less than or 1 over r prime, over C. And we said that if the observation point is very large compared to R prime, which is the far field limit, then that's close to what we have for radiation, unless things are going very fast. So especially if you're going not too fast compared to speed of light, then far field approximation is pretty much the radiation approximation itself. In that approximation, we said, well, we wanted to find out what is the electric field here. Instead, we started with the magnetic field multiplied by C. Asking, given the charge distribution here, what can we say about the electric and magnetic field very far away in the leading order? That we said was minus. So no, check the sign here with respect to what I said last time. This is mu naught over 4 pi times 1 over r cube r prime, and I had time derivative of j. So let me write this as t of r, right? So this is t prime, r prime, comma t prime, and then evaluate this at t prime is equal to t minus r over c plus r hat dotted with r prime over c. Is that all within the board space? Yes. This is what we often call the retarded time. Let me say that's t of r. You can also write this quantity in the curly brackets as d by dt, oops, of j of r prime, comma t r, right? That's also perfectly okay. Check the sign here. I'm not sure if the last expressions that we wrote down, whether I wrote the sign correctly last time or not. Maybe I did, because I called this whole thing as a function k. And that's the point here. Last time, I think, I think the difference was that I introduced the negative sign in the k. So instead, I can say this is minus r hat crossed with whatever is after the cross sign. I will call that k here. It's a temporary notation. It's just so that you can identify what your magnetic field is in terms of the sources. Sometimes it is also good to write only the integral as your source and see the 1 over r potential explicitly showing up there. That's also a good item. We said that the electric field, similarly, is, since I took out this negative sign out, that will be, we showed that that's equal to r crossed with the magnetic field, C times. The advantage of writing C with the magnetic field is that the dimensions of electric field and magnetic field times the speed of light comes out to be exactly the same. So there's a check on the dimensions in an intuitive manner. One can check one thing right away, and that is that what happens if you were to take r hat crossed with E. You notice that this is minus of r hat crossed with, so electric field is minus of this, so this is r hat crossed with C times B. Use the back-cap relation, and you could learn that this is equal to minus r hat dotted with B plus r hat rh squared, so that's C times B. But r hat crossed with B will be 0 because it was given in terms of a cross product with respect to R hat. So that's equal to 0. So we learned that the vector R crossed with the electric field is also related to C times B. And this way of writing it, that clarifies that, oh, the magnetic field is perpendicular to R and E, electric field is perpendicular to R and B, and all this together suggests that the vector R, electric field, magnetic field, these all three are perpendicular to each other. And that's what, remember, happens when you're dealing with a monochromatic wave. Right? There is a direction of propagation, electric field, magnetic field, and the idea is that radiation fields are or the electromagnetic waves that we studied at introductory level are produced by radiation. Right? So they are always produced in this manner. You don't have a choice. They will always come out this way. So where does this stand? If you were to draw it in this perspective, we have a k vector, so it could be anywhere. So let me draw it somewhere at an arbitrary point, and it could even be coming out of the book. Right? There is some source contribution, the overall source. If there was a single point charge, that's different. There will be a single k, but at whatever it is, overall there is a contribution k coming in. That's from the complete integral. And if it is out of the plane, rotate that a little bit. If you have two vectors, vector r at k, you can always put them in a plane. And once you have them in the plane, r crossed with k gives you b, right, with a negative sign. So it has to go in. So that's your c times b, or direction-wise, that's just the magnetic field. The moment you have that, r crossed with the magnetic field, again with a negative sign, that gives you your electric field. And again, think of a monochromatic wave. If it was going that way, you will always know that electric and magnetic field are aligned using your right-hand rule, right? So electric field crossed with magnetic field should give you the direction of propagation. So that's your basic property of the radiation field. And now the only difference between what you have studied in introductory physics and now is that here you have an actual source of the magnetic field. So we can say that, okay, what can we do? If you want to design an antenna, you would provide a source there. So current, provide an actual current there, do this time derivative, do the integral, and you know exactly what is going to be the magnetic field. Here, today what we will do is, instead of actually giving the current distribution, we will just start with a point charge. Let's say that it's just one point charge moving around. Remember, current is a series of current charges moving around with a certain velocity. But today, let's talk about just one point charge. But before that, most of the time, we are not interested in the electric and magnetic field itself. What we are interested in is the energy. Right? How much energy is there at some observation point? It is constructed out of electric and magnetic field. So let's talk about what is the energy at some distant point. And remember, for that, last semester we did what was the charge density and momentum density. So we defined what was the Poynting vector, so flux of energy. Remember, so the flux of energy was defined as, so this is energy per unit time and per unit area. This was defined as S, and this was a time dependent and position dependent quantity. Right? This was also called the Poynting vector. And that was E crossed with H. But we have our expressions in terms of electric and magnetic field, B, not the H. So H and B are related by mu, remember? So we have, this will be 1 over mu naught times the electric field crossed with the magnetic field. Again, electric and magnetic fields are position and time dependent. We don't even, whenever we say this is per unit area, this is at a very far region relative to the sources. If we were to put that onto the right side, left-hand side, whatever we have left out is your power, which I will write as dE by dt. Now, at this point, electric field, remember, is also using the letter E. I can use du if you want, but let's use, I think it won't be much of a confusion here. Let's use the letter E for energy also. So be careful that you're using a letter E for energy and the electric field. Hopefully in the context that we are talking about, it will be clear what is what. This is going to be equal to, so this is power. So I'm putting the area on the right hand side, and let me integrate over all of region, or better, this can also be, so let's say, so this is per, yeah, so this is equal to, let's say this is d omega, or let's say the area, right, the A dotted with E crossed with H. Okay. Let me integrate that also over the whole, in principle, any surface area, but let's me choose the surface to be right at infinity. That means to say that dome that is completely enclosing the sources, which is very far away. So this we will say is r squared. So that's the radius, and the omega, now that is a unit vector which is in the direction of r hat. So what I've used is dA is equal to r squared d omega r hat. If I put my origin somewhere in the region of sources, since my observation point is very far, the explicit points are not relevant, so it's r hat times r square times d omega, and dotted with E cross with H. One might think that, oh, this is r dependent, but notice electric field has a 1 over r in it, magnetic field has a 1 over r in it, so that r square actually exactly cancels out, and even at infinity, at a very large distance, you still have a power contribution. Let's evaluate that nicely. Oops. I think this was 1 over mu naught E crossed with B. Okay. So we have the power or energy. So you can also say this is power. Power is the energy per unit time. That's equal to r squared d omega times r hat dotted with E cross B. E cross with, yeah, E cross B. Later, we will be interested in the angular distribution. For example, you want to design a source of electromagnetic wave which is very oriented, like you want only certain people to listen to what you're communicating in a certain direction. Then you will be interested in the angular distribution. Then you want to release this integral and put it on the left-hand side. We'll talk about that later. But today, we want the total power are radiated, and that will be equal to r square. This is d. Okay, let me actually, for the time being, put this on the left-hand side, right? So this will be better off written as d2e times dt and d omega. So that's energy per unit time per unit solid angle is equal to r square times r hat. Replace the cross and the magnetic field. Let's dot it with B. That's a well-defined object. But R crossed E we saw was equal to the magnetic field itself. And that gives, so the R cross is magnetic field itself, or it was C times the magnetic field. So that's R cross times C times magnetic field dotted with D. Oh, I missed something, right? So I think there was a mu naught in there in the definition.
That's what I was wondering when we went from H to B.
Yeah. Good catch. Yeah. So let me go back and fix that. So here I defined, when I went from H to B, I introduced a mu naught, but then when I wrote the actual power, I dropped it. So let's keep that mu naught. And sorry, so now this is B. Oh, this one was okay. It's just that later on, but this is all okay. Yeah, this is all okay since I wrote it as H. But when I switch from H to B, I have to introduce a mu naught, right? So this is 1 over mu naught, and that is a 1 over mu naught here. And let me write a C here and 1 over mu naught C, because I have the expression for magnetic field. This is nothing but 1 over mu naught times C and R times CD. Square. We're going to square something, it's just the square of that quantity. And notice our magnetic field had a 1 over R potential in it, so that exactly cancels out. So what is C times P here? So this is equal to, let's see, this is, where was that? Yeah, so this is, since it's a square of mu naught times C, and I have R hat crossed with mu naught over 4 pi. This is magnitude square, right? So this is d cubed R prime. And let me write this as d by dt of J prime, comma, of T minus R over C plus R hat R prime over C. And I will square that. That's your total energy per unit time per unit solid angle. And that's your total expression there. And since this is a cross product R crossed with R, I can maybe simplify this a little bit, but I'm not sure whether I want to do it at this stage or not. Let me check what exactly I want to pursue here. Yeah, so it's okay.
Dr. Shudish, I did have a quick question.
Yes, please.
It's probably it's minor, but in the K vector, Why is it not dependent on r prime and t prime?
Because I do the integral, right? I think your question is there here, right? Here. Here, right? This one.
Yeah.
And because after I do the integral, there is no r prime remaining, right?
Okay.
Right. So this is just dependent
Just the
on
1 over r. Okay.
1 over r. And t prime is not there because I have t prime is not there because we said this was t prime is equal to t minus r over c, right? Plus. So t prime is just a like dummy variable here. I used it to substitute something. So the time dependence is in t.
Okay.
After I do the integral, like as an observer, the observer only knows about r and t. It depends on the position of r prime, but they're all added up. Right?
Okay.
After you add up everything, there is no source dependence.
That makes sense.
Like it's not that it doesn't depend on the source there. Yeah, it will depend on the source dependence, but unless you specify that, if you have a single point charge, there will be the position of the charge sitting in there, and that's inbuilt in there. So I haven't shown that. So maybe one should say source points, right? So this is source points. And having said that, like remember again, we are so far away that you don't see the details. Relative points you won't see, so that approximation is in there.
Okay. Thank you.
And it is 1 over, if you're interested in the 1 over potential, then you don't worry about it. So it's more than just saying that it is not accounted for, it is not there. If you're, otherwise the energy will go to 0. If it is not the 1 over r, you go to the higher order term, then the energy will go away. So that's a little more good point, yeah. So think about it. Yeah. But yeah, it's not there. Okay. So with that, so we have here. So let me rewrite this little. I want to put this mu naught over 4 pi out there, and I want to get the units of this straightened out a little. So so let's write this as yeah. So let me pull out this mu naught. So what we have in front is 1 over mu naught times c, and that is a mu naught over 4 pi the whole square, which is the same as 1 over 4 pi or mu naught over 4 pi square. Let me write this as, remember mu naught is same as 1 over epsilon naught times c squared. Did I get this right? Is that what I want to write? Yeah, so this is surely one way of doing this. So, oh, there is one C I missed, is it? So there is a C here, right? Yeah, so that's C cubed. So that's equal to 1 over 4 pi epsilon naught times 1 over 4 pi C cubed. Let's write it this way because the final expression we will be writing, which will be called the Larmor formula, is written in this form. So our our expression then is so just rewriting our expression. So we have d2e over dt d omega is equal to 1 over 4 pi epsilon naught 1 over 4 pi c cubed, and the whole thing without the mu naught over 4. That's the complete expression. And if you have a general charge distribution, then you want to keep that. But what we will specialize into at this point is a non-relativistic limit. This is going to be a non-relativistic limit. And that is to do with all the velocities of the charges are going to be small compared to the speed of light. And this is good as far as you're not talking about like if you're in the Fermi lab or if you're in CERN, there the charges really go very fast, or if you're talking about cosmic rays. But whenever you're talking about a radar or a current carrying wire, in those situations, non-relativistic limits are good enough. And what it does is for us is that allows us to neglect this piece. This piece will be neglected. So drop that. So that's a higher order effect. So we don't get contributions from that. Let's think of a single point charge going about in this manner. So this is d cube r prime time derivative of j r prime t minus r over c now. So there's only one piece in there. Remember now, let's say we have a single point charge moving about, and that will be equal to q times, that is the velocity in here, so that's d by dt of the velocity of the charge itself. So this is now the velocity of the charge that is coming in, and that's just t minus rc. So the only point we have to remember is that whatever is the velocity of the charge, it is in the retarded time, right? So this is t of r. And now this partial derivative is actually the time derivative itself. So that's q times acceleration of the charge. Except this is at the retarded time. So we call that t of r in the non-relativistic limits. I'm getting rid of the second. Later, in another place, probably in a slightly more advanced course in your electromagnetism, you will capture the second piece also, the relativistic case also, and that's not very hard to capture. And I should also tell that if you were to think of your dipole moment, magnetic dipole moment contributions, all these can be nicely distributed into, there is a contribution from the dipole, there is a contribution from the magnetic dipole. Each piece of this charge distribution contributes. So those are all, we won't get into the details primarily because we don't have the time. But from starting from this expression in very quickly, you can get those results. Here, let's concentrate on, if you were to interpret this whole thing as an acceleration, how do we get our result, right? Or how do we get the power associated with that acceleration, with that accelerating charge? So, so what we have, an accelerating charge, accelerating charge, let's say, seems to have a contribution of energy radiated per unit time per unit solid angle is equal to 1 over 4 pi epsilon naught times 1 over 4 pi c cube times r hat crossed with acceleration evaluated. Let me insist, or let me clarify that this is, when I write dr, it may not be visible. So this is evaluated at the recorded time. So that's square of that quantity in there. Let's see how much is this. Oh, did I miss something? There is a charge, right? So there was a charge also. So this is q times that's q square times that quantity. Let's think of a particular situation where you have an accelerating charge to be in this direction. That's that. So a charge is accelerating, not necessarily moving in that direction. Remember, motion itself need not be in the direction of acceleration, especially if it is going in a circle. It is actually perpendicular, right? So this could be you are pointing towards the center. The charge could be moving in a circle. And let's say, with respect to that, you have an observation point. That's your r. That's your r. So r hat will be in that same direction. And let's say this is our angle. So it is clear that the cross product will have a relation to this. So this tries to tell us in what angle is the radiation going to be the largest due to this point charge. So it's clear that QE over ET times d omega is now, all these are constants, notice. Pi c cube, and magnitude of r is 1, magnitude of acceleration t minus r over c, magnitude comes in, not the direction, and the direction is contributing as a sine square theta. So if you want in each solid angle how much radiation is going in, it is getting a weight of sine square theta. Clearly, if you are accelerating a charge and you measure it in the direction of the acceleration, angle theta is equal to 0, you won't see any radiation. So radiation is maximum perpendicular to the acceleration. So if the doesn't matter what direction the charge is moving, if the acceleration is this way, radiation will be the largest in that direction. Imagine easiest way to think of is that if you have a rod and you make a current go in this direction, you make the current oscillate. That's an easy thing you can do if you want to have a simple, what do you call this, antenna, or this is a emitting antenna. You make a current that makes the charges go this way. You make an oscillating current, so it is accelerating. If you make it go in the same direction, then you don't get acceleration. So since you want acceleration, you make it go back and forth, right? That provides acceleration. But then the radiation will be maximum in this region, and usually you show this radiation in this form. So we'll talk about those things later on. So in the perpendicular direction of that oscillation is where you get in the maximum radiation. So that's the sine square theta contribution coming in. But let's see, what about the total? There is more radiation in angle perpendicular to it, but let's calculate the whole radiation. Let's add it up all together. So integrate over all the solid angle. So that gives us a power, right? So power P is equal to dE by dt is equal to, integrate over the whole solid angle. This is all constant. And let's also say that the acceleration anyways, it's the magnitude that is contributing in. It's not going to depend on the theta. So this is equal to 1 over 4 pi epsilon naught. And this is q squared over 4 pi c cube. And let's just say this is aq squared evaluated at the retarded time. So let's say this is the retarded time. And now we have to integrate over the solid angle. So that's 0 to 2 pi d phi and 0 to pi sine theta d theta, and that is sine square theta. Notice this is your solid angle, right? Solid angle comes with the weight of sine theta because it's a sphere. It needs that weight of sine theta already. So that makes it an integral of sine square theta. Let's see what that is equal to. Substitute sine theta is equal to cosine theta. No, substitute cosine theta is equal to t. And that allows us to write minus sine theta d theta to be dt. Okay. So then this integral becomes over 4 pi epsilon naught q square over 4 pi c cube q square. Phi integral is trivial, so that's 2 pi. And after the substitution, this becomes dt. In fact, it's a minus dt. When theta is equal to 0, t is equal to plus 1. And when theta is equal to pi, t is equal to minus 1. And this is an integral over 1 minus t squared. The sine square theta is 1 minus cosine square theta. And that's 1 minus t squared. The negative sign can be used to invert the limits. And that's a straightforward integral. So it's q squared over 4 pi c cube. Acceleration q squared 2 pi times what is this integral? So this is gives me a t. So let me do that here. So that's a t minus t cubed by 3, and I have to do that from minus 1 to plus 1. Move that a little bit here. Yeah. So that's 1 minus 1 by 3. So that's 2 by 3 when you evaluate this because it adds up. Right? And then you have to multiply it by 2, right? Because there are 2 pieces coming in there. So it's 4 by 3 basically. So that whole integral is 4 by 3. There is a 4 pi that cancels out, and we get a very closed form solution for this total power emitted by an accelerating charge, which depends only on the acceleration, only on the magnitude of the acceleration. Q, it's written as, so 4 cancels out, so that's a factor of 2 by 3. And acceleration AQ, so this is evaluated at the retarded time divided by CQ. And this is called the Larmor formula. And it tells us that if you have a charge that is accelerating, it will radiate. And that immediately tells us that if you have an electron that is going around a circle, which is basically a hydrogen atom, is going to radiate. And that's what your homework is. And let me quickly Now, what that is, so we have dE by dt here is proportional to, let's say, so there is a constant there, and is proportional to acceleration. And for a circular motion, the acceleration is v squared over r. Right? So it's square of that. So if you have a charge moving around a circle, that's centripetal acceleration, that's v squared over r. If you're talking about a hydrogen atom, we also know that the force, so you have a positive charge and negative charge going around in a circle, this force F, which is an electrostatic force, has to be balanced by the, or has to be exactly equal to the centripetal acceleration. So mv squared over r, that's your acceleration, has to be equal to 1 over 4 pi epsilon naught, the force, right? So that's q squared. For a hydrogen atom, it is electron squared. So this is electron squared divided by r squared. So we get an expression for velocity square. Velocity square is proportional to 1 over r, right? R and r cancels out, except for the constants, it's proportional to 1 over r. So v square is proportional to 1 over r, and there's already an r, so that's about 1 over r raised to 4. And you go, so as time goes, there is so much radiation happening. So you want to talk about, so this is energy, and let's say this is proportional to dt over r raised to 4. Put it on the other side. Let's say that is dt is equal to r raised to 4 times dE. Or actually, you want to first convert this into r, right? So I want to first write it in terms of yeah. So we want to first convert this into radial motion, right? What's the question? Let me see. I don't have the question, I guess. Yeah, I think you say this. What was the question? Do you guys remember? Have you guys?
Yeah, I just pulled it up right now. It says an electron of charge E and mass m moves in a nearly circular orbit under the Coulomb forces produced by a proton. Suppose as it radiates, the electron continues to move on a circle of ever decreasing radii. And then it goes through A, B, and C. C gives the equation of motion. mv squared over r is 1 over 4 pi epsilon naught. E squared over r squared. A is v squared over r. Can we just share my screen so you can see what you need?
No, I just yeah, I think that'll help. Yeah, go ahead. I think I was trying to open it myself. Yeah, okay. Yes, I see. Yeah.
Oh, you have it. Okay.
Yes. Okay. So the idea is the following. Okay. So this is giving you dE by dt is 1 over r raised to 4. But we can also write our energy starting from here, right? For the hydrogen. This is the general Larmor formula, right? This is Larmor formula. For hydrogen atom, so for an atom, we also have the energy to be equal to half mv squared plus the potential energy, which is 1 over 4 pi epsilon naught times 1 over r. But v half mv squared is again related to r, so this will come out to be one can show. So this will be equal to 1 by 2 times use your potential or centripetal force in here. So this is equal to E squared over 4 pi epsilon naught times R again, right? Using this in here. So it's minus 4 pi epsilon naught 1 over R, which is equal to minus 1 by 2 times 4 pi epsilon naught R. That's your energy. Again, change to dE, calculate dE by dt from here. So let me actually, where is this? Where are you guys? I think okay. Start again from here. Notice this was the expression using Larmor formula. For the atom, dE by dt would be equal to, there's only R that depends on time. So this is equal to 1 by 2 times 1 over 4 pi epsilon naught. Take a derivative, so that's 1 over R squared, and the negative sign goes away there, and that's dR by dt. So that was that's one of the problems, part in your problems. Use this up there, and what you get is you combine these two, right? And you have to put in all the constants. That's part of your homework. If you go through the details, you get in all the constants also. But when you put these things together, what you have is 1 over R squared dR by dt is proportional to 1 over R raised to 4. Cancel the R squared, so this is basically 1 over R squared. That's what you get in. You can integrate on both sides. So what you can do is R squared dr is equal to dt. Right? That's what you will get in there. Integrate this, but now here is the point. You start from the radius of an atom. So radius of an atom, so atom radius. And as time evolves, since it's going to emit this energy, the expectation is that the radius goes down and eventually it will go to 0. And that will happen in a finite amount of time. If it takes infinite amount of time, that's good. Then your atom is very, very stable. If you start from time 0 and let's say you go to a certain extent time. The left-hand side integral will be easily doable, and the right-hand side integral gives you the time it takes for the atom to collapse or basically decay, if you want. So that's a measure of the lifetime of the atom. And you will notice that it's really tiny. And that leads to the conclusion that your atom is unstable. So it's a nice kind of physical picture you get connecting the radiation and the stability of the atom. And that led to quantum mechanics. So that's why I feel that's an important problem to ponder about. But yeah, go through your homework. So all the steps are given to you. You just have to follow the steps and think about what's going on and read about it if you want to. Okay, I'll stop here and thank you.
Dr. Shardish, I was wondering about the retarded time a little bit.
Yeah.
Is there some sort of like, I guess, physical intuition, like if you're thinking in terms of relativity? It seems like, with T minus R over C, you're canceling the time that it would take for light to travel to the observer from the origin, and then you're adding back some other time based on R prime in the direction of the observer. Is there any sort of like, I guess, intuition or like a physical kind of like get there from relativity, derive the Green's function for how we got there, but like could you get there without like just by using like the idea of relativity in a sense?
Okay, I think maybe that is a misleading point or okay. As far as retarded time goes, this is the exact expression. Okay? no approximation, like V, okay, so maybe first let me write this down. Over C. Is this visible? Yeah. That's your exact expression. And that works with the idea that there is a source at R prime, and it's the amount of time it takes to reach from R prime to R, which is what you said. That's exact. And that is the physical intuition.
Okay.
If you want to make an approximation, then this is also equal to T minus R over C. It is like saying that if you had an origin, your charge was actually here, that's your R prime. There's a small time difference, right, which you have seen in your project actually, right? So that's that same approximation. So if you were to neglect this, that's your piece still, that's the main piece. But then you get a correction from here. Like this is the correction part. That's your R hat dotted with R prime dotted with C. That's the leading order correction if you want.
Okay.
But this is the correct one. This is the correct one. So no doubt about it. This is your actual point. So that's everything. That's the physics of it. As far as relativity goes, it's the time taken for light to go from source to the observer. And it goes like a light, notice. I mean, if you want, if I want to add on to it, this quantity, there are two events, right? There is an emission and an observation. Those two events are connected by a light-like distance. So remember, there's a time-like, space-like, and light-like. So it's a light going through, not an actual particle going through. Does that help?
Yeah, yeah. I think I was focused too much on the approximation. I think it's more clear actually with the exact. Yeah. Okay. Yeah.
Okay.
Thank you. Yep.
Yeah.
That makes sense.
Okay, good. And Christian, one more thing. I think Saikat Talapatra pointed out to me that he has apparently opened the course.
Oh,
So-
okay. I hadn't seen that last time I looked. I'll get back on and register.
Yeah, just for your information. And remember again, 2, okay? Only
Yeah,
2.
2 credits.
Yeah.
Yeah, I talked to Tushari. That'll help because if I can't fit thermodynamics in, or no, my other elective, what was it? Solid state physics 425. If I can't fit that into my schedule in the spring, then Tushari said that she would be able to kind of teach me through the material for like a 1 or 2 credit class where I would just meet with her outside. So yeah, that would be still helpful.
Okay, sounds good. Yeah. And again, remember, if you have 1 or 2 credits needed, then you can register with Dr. Talapatra. That's what he said.
Okay.
But with me, you can have only 2. So it has to do with how much I can do in a 1 semester. There are limits to that. Okay.
Yeah, that's totally understandable. Thank you though for doing it.
Yeah. Dr. Talapatra did everything.
Yeah. I'll talk to him again. But all right, thank you.
Good. Yeah. Hello, Bowden.
Yeah, I just had a quick question on the homework.
Sure.
I just want to make sure. So, like, for part B, it states the Larmor formula. We don't have to calculate anything for part B. It's just stating the formula that we use for part C. Is that
charge that is the law. Yes, that's correct. So it is just a statement. You don't have to do anything.
Okay, yeah, I was just a little bit confused about that.
No. Good point. Yeah. Sometimes I make these questions as if they are like reading through a chapter, and sometimes it gets confusing as to what is asked in this, especially if you make a special point there. Yeah. Good point. So you don't have to do anything. Just write down that same.
Yeah, that's what I figured. Okay.
Yeah. Thank you for asking.
All right. Yeah. Thank you. All right. Have a good weekend.
You too. Bye.